All right, go ahead and get started on the warm-up. Sorry, a little delayed there. Use the following hash code function to take in these pairs you're going to put into this hash map. So, you need to pass the int key into this method. The key is divided by 100 and then mapped to a correct index of the array, which is where you mod it by the array size. This array size is 10. So that's a very convoluted way of saying, take all of these ints, divide them by 100, then mod them by 10. Use separate chaining to resolve the collisions. Go ahead and take 3 minutes, fill it out. The poll everywhere should be live. Jesus. Okay. All right. I've seen the amount of gesturing start to slow down. Wow. Now the microphone feels so hot. Turn that down. Okay. Let's play the poll everywhere game. Let's play that game. Let's take a peek. Okay. Let's see. Oh, no, I don't want that. Okay, fine. To actually exit presentation mode. Let's see here. Aha, interesting. Okay, we've got sort of a dead heat between 2 and 4. Good. I was trying to put some tricks in there. This means that I have tricked at least some of you. Oh, but somehow in the awareness of ourselves within a community, we change who we are. Interesting. Listen, majority rule isn't necessarily always correct. But it does seem to be happening in an interesting direction. Okay, hang on. I'm going to exit. I'm going to reactivate it. Okay, let's dig into this. So let's just sort of put these in bit by bit. Our very first one is the pair of 1 and A. If you can't tell, the values have no say in where they go. The values are just passenger princesses along for the ride. So it does not matter what I made any of the values here. Let's just talk about the keys. So for a key of 1, does any brave soul want to tell us which index that hashed to for them? Yes, congrats, first one. 0. I agree, because 1 divided by 100 is what? 0. And then 0 mod 0 is what? Aha, okay, great. All right. Does someone else want to tell us where the pair with 5 is the key wind? Where are we going? Yeah, here. Also 0, I agree, because 5 divided by 100 is what? Hint, it's the same as the last one. That's why there's a collision. 5 divided by 100 is what? 0, amazing, wow, okay. And then 0 mod 0 is what? Okay, great. Maybe rhythmically challenged, but that's fine. Okay, let's talk about the third one in my little sequence there, 100. Does anybody want to tell us which index 100 map to for them? Yes, here in the middle. 1. I also agree. 100 divided by 100 is what? 1. And 1 mod 10 is what? 1. Oh, and that's where it ended up. Okay. Let's talk about the fourth one, 555. Does anybody want to tell me where that one hashed to for them? Yes, please. 5. Yes, I agree. Because 555 divided by 100 is what? 5. I'm trying to help you. 5. 5 mod 10 is what? 5. Yes. Okay. Now, let's talk about the 1,234. Does any brave soul want to tell us where that one ended up for them? Yes. 2. Aha, yes. Finally, the mod really helps us wrap around. So 1,234 divided by 100 is what? I'm going to guess you got it right at least. 1,234 divided by 100 is what? 12. 12 mod 10 is what? 2. So see how we first translated it into some hash, which was 12, but then we mapped 12 to an index that fit in our given array. Questions on that one? No, we understand it perfectly? Amazing. Okay, then what about 8,675? 8675. Yes. 6. Interesting. Okay, so 8,675 divided by 100 is what? Correct. And 86 mod 10 is? Love it. Wait, I forgot to click for the last one. That was less dramatic. Okay, my rhythm's off. There we go, but correct. 6. Okay. 309? 309, anyone want to tell me where that one ended up for them? Yes. Your wonderful hand gestures are correct. I'm going to give you the credit. It's 3. And the reason it's 3 is 300 divided by 100. 309 divided by 100. I can say things. Is what? 3. 3 mod 10 is what? 3. Amazing. Okay. And then our final one, 12,345. Which index does that end up going to? Aha. Yes, I saw another bunch of hand gestures. You're also correct. Okay, so 12,345 divided by 100 is what? $12.3, I think is what I heard the murmurs. And correct if we were putting it into a calculator, but this is Java and we're doing ints. So even though it might hurt your math brain, if I am asking 12,345 divided by 100 is 12. Love it. Thank you, friend. Yes. We just remember, we don't round up, we don't round down, we just drop the integers. Yes. Question? 123. That makes more sense. Thank you. Correct. I can do divisor. Okay. It's 123, right? 12,345. That's 123 hundreds. We can do math. Thank you. See, you don't need to know math to be an engineer. There you go. 123 mod 10 is what? 3. Amazing. So if you can start to see a pattern that I mess up, is when you divide by 100, it's like you just sort of chop off the last 2 digits, like the 200s digits, right? So 12,345 becomes 123. 1234 becomes 123, right? Or 12, sorry. And then mod by 10, that's you divide by 10, and then you take the remainders, right? I don't know what that is. Any questions on how we did any of this stuff? Yes?
I just want to make sure the mod, which comes from map to value index function.
Yes. Map to valid index function is where the mod comes in. Should I have put it on this slide? Probably, but I was running out of time, and then I did that teacher ex post facto justification thing where I was like, oh, it's kind of a test. Do they remember? Whatever. I'll decide how you feel about that one. But yeah, remember that hashing is the act of taking any value and translating it to a deterministic representative number. In this case, that hashing is dividing by 100. But once we do the hash, we then also always need to mod by the size of table to make sure that it actually will fit in the table at a certain index. So there's always sort of those two separate steps. One, get some representative number. Two, mod it by the table size. Yes, question? What if we had tens instead of 100? Like if I... Oh, just what if we did number 10? Okay, so 10 divided by 100 is what? 0. There's no 100s that fit into 10. And then 10 mod 10 is what? 0, because 10 divided by 10, it fits perfectly, 1, so there's no remainder, so our mod is 0. So something 10 would go into index 0. And in fact, anything under the value of 100 would map to index 0 for the same math logic. Lovely. Yes?
So the convention for map hash codes is first you divide and then you get mod by the table size?
So this is not a convention. This is just some math that Casey made up in that divided by 100 thing. The mod by table size, that is just a requirement to make your hash tables function. But I just made up a hash code that I was like, take the number, divide it by 100. In fact, this is a really, really crappy hash code because you're going to get a lot of collisions just dividing by 100. Yeah. But I wanted something, I don't know, to annoy myself with basic math at the beginning of lecture, I guess. Any other questions? Cool. One thing I just wanted to address. Shout out to all of you. 2 is the correct number of collisions here. 4, I think that happened if at some point you were doing divided by 10 instead of divided by 100. I know I did it wrong, and that's how I got there, so there's probably some math stuff. But this, nope, there are not collisions in separate chaining point. I just wanted to make sure that we clarify there are collisions in separate chaining, but instead, the way we handle the collisions is we just let every single index of the array become a bucket that can store multiple things. So the collision resolution strategy for separate chaining is to just let that bucket hold as many things as it wants. That doesn't mean there's no collisions. It just means the collisions are all going to hang out in that singular bucket. And in fact, today we're going to talk about open addressing and other ways that you can resolve collisions. Okay, great. Not any particularly interesting announcements. Exercise 2 is due tomorrow as per usual. Project 2 is already out. Please hear me, start early. It will be crazy at office hours next week because we not only have this assignment due, but we also have a midterm next week. So I suspect next week will be busy for you. And this is me telling you, be a better student than I was. Start early, okay? This is the week. Because I know y'all have other midterms next week too. Why? Why do you all do that to us? I don't know, because I've tried every which way to not have a midterm in week 5, and I can't make it happen. Okay. Also, I think group work makes us all better people because there is no work in this world but group work, and I unfortunately, can do nothing to assist you in your relationships with other people. That's your business. So I'm going to say this one thing here. I got a lot of charmingly stressed out emails this weekend about how partners were maybe not carrying the appropriate load. I know, when it's a partnership, it's really evident if somebody's not carrying their load. So this is what I'm going to do to help all of you. hey, you don't have to have the same partner project to project, right? And like, if you don't want your project partner to feel like they got to go find a different partner, be the partner you want to be. Because they're not married to you, so they can possibly abandon ship. You don't want them to do that. You want to be a cool partner. You want to have a great partner and a great partnership all the way through the course, right? And if you are sitting here thinking, oh my gosh, my partner was not a great time, maybe try having a conversation with them and being like, Casey reminded me about it because she said we could switch partners mid-class. Cool? Okay, that's all I want to say about that. Y'all are adults, figure it out. Okay. But enough people emailed me. Okay. Okay, the first few slides in the deck today are sort of things to help you with your project 2. Remember, you are implementing a chaining hash map. So one thing that I notice is really, really difficult for students is, one, figuring out how to iterate through the hash map. Because remember, we've now got a collection of collections. We've got an array of linked lists. So you're going to have to implement an iterator that will know how to move not only across the different buckets, but within the certain chains. So keep an eye out for that. Draw pictures, go to office hours. This is all just stuff for you to read. The one thing I did want to make sure that I mentioned, because this is the other most common issue I see in Project 2, is not rehashing when you resize the array. Remember how there's 2 phases of where something belongs in the hash table? There's the get hash code function, and then there's the mod by table size. So if you run out of table size, or you appropriately resize when, say, lambda is 1, or whatever you choose it to be, you need to go through all your keys and rehash them, because you're going to need to remod by the new table size. In fact, if you are getting an array that looks like this, where you've got this massive cluster of things in the top half and then just a bunch of emptiness at the bottom half after you resize, that is a red flag that you have not rehashed. The point of making a new array that's twice the size is so that you can spread out the entries, cause fewer collisions. But that's only going to happen if, when you resize and you go through and you're ready to move everything over, you use that iterator and you start at the first thing and you say, okay, 1, red. What's the new location it's going to end up? Apparently it stays in 1. But 6, pink, well, that ends up down here. And then 22, tan, that ends up over here. And 7, blue, that ends up here. So you still have to rehash everything at the resize moment. Any questions about that? If you're already at this part of the project, I will be very impressed, quite frankly. So that's why I'm trying to say it to you before you get stuck on it. Great. Okay. Okay, so we were sort of talking about non-integer keys at the very end of lecture on Friday. I just want to make sure that we actually talk about these things because it is on your exercises and all that fun stuff. But remember that a hash function, by definition, is just any function that maps data to fixed sized values. So it's just something that takes in a piece of information and translates it to a certain fixed set of integer values. This can be applied to any type of object. We've mostly been looking at ints, and I think I snuck in a couple strings, but it could apply to anything. And in fact, any type of object you want to be able to put into a hash table needs to have its own get hash function. I don't think this is the most interesting practice. We're going to skip it. Sorry. But you can go do it if you want to, in your own time. But let's talk about some hash code functions. So I think I was showing you this very quickly in lecture on Friday. Remember that if we have 0 collisions, that's when we have that perfect constant time lookup, constant time put. So we are always trying to reduce the number of collisions. One way to reduce the number of collisions is to have a bigger table. Another way to reduce collisions is to change how we generate that hash code number that's representative of our value. So we could have a hash code function that maybe just calculates like by the length of the string. That's a way to go from any string to some number, just its length, right? It's super fast, as you can imagine, because it's just a field somewhere that gets returned, but this is going to cause a lot of collisions because according to this type of hash code, the words cat and hat and tack and, I don't know, bat all would have the same hash code for 3 because we didn't incorporate very much about our piece of information in generating this hash code. Fast, but lots of collisions. If we look at the second one down, what we end up doing is we take in a string, we loop over, and for every single individual character, we cast that character to an int. This will give us back the ASCII value, and it depends on which encoding you're using, but every at least like Roman character, lowercase a through z, uppercase a through z, punctuation and numbers has an ASCII number. There are Unicodes so that you can use, obviously, non-Western and non-Roman characters as well. But we loop through all of those. We cast them to some magical number that's representative of it in the computer. And it's still really fast, but what we've done is we've sort of summed up the character totals within a single string. So now hat and dog will not have the same hash number, but maybe like dog and God will have the same hash value because they're anagrams. Is that the word for that? So, depending on your data set, again, we're talking about the trade-off. Like, okay, it's pretty fast. It is not running, it's running in like sort of n time, linear time, where n represents the number of characters per word, but maybe all your words are pretty short. Tough to say. Then you could take it to like the extreme level where you actually calculate based on where something's position is within the string, and you also introduce a bunch of prime numbers. But the act of calculating prime numbers, I'm assuming, has traumatized all of you from last week and is very expensive. And so this one is likely to cause the fewest amount of collisions, but cost us a lot along the way. And like we just talked about, you have to call the get hash function every time you want to put something new in the collection, every time you want to get something out of the collection, and every time you need to resize the collection. So you don't want it to be overly expensive because it's going to be the method that gets called the most in a hash table. Questions about this? Sure. What a fabulous question, to hash something and then hash the hash code. Foreshadowing. Last slide in the deck. Love it. Any other questions? Okay. In case this is a question that comes up, good hashing, then we're trying to accomplish sort of 3 important things. One, that it is deterministic. The same input should always produce the same output. That way, when somebody asks me later if that thing's in your collection, I get a deterministic response from my hash code. So like this one, where you just generate a random number, not helpful. Because if I say, put a key in that's, let's say, the key of Apple, and then somebody later is like, hey, is Apple in your collection? Well, I can't reverse engineer how I got the original hash code to go and find it if I just use random numbers. So I need something deterministic based on the value. Then I need something that's relatively uniform. And what that means is that we don't have these sort of collisions or these clusters around certain values. Because remember, we're trying to get to that perfect one thing per each index hash table, constant runtime. So uniformity, that gives us sort of a distribution of values or a diversity of values. And then finally, efficiency. We want it to be rather quick. Otherwise, our hash table is going to be slow. And that is literally the opposite reason that we would use a hash table. The goal of a hash table is as quick a lookup, as quick to add something to your collection as you can get. Okay, here's a good practice. Look at these 2 hash code functions and discuss with those around you. Let's say take 2 minutes. Which one will produce more collisions on average? Go ahead, chat for a little bit. Okay, let's chat about it. I will tell you, these are both crappy pieces of code. I did that on purpose so you have things to argue with one another about, because they're both really bad hash code functions, as it turns out. But does any brave soul want to tell us maybe some of the things they discuss with people around them? What's one thing we think maybe contributes to the collision rate of something here? Anybody have a vote for which one they think causes the most collisions? Yeah, sure.
I think the one on the right caused the most collisions.
Okay.
Because I think on the line that starts with results, the one on the left is more complicated.
Mm-hmm.
It multiplies the value there by 37 to the I power.
Mm-hmm.
In addition, the return statement says result by modulo 5, whereas the simple one on the right just says return I.
Yes. So there's a bunch going on here. So I agree, for example, if we look at what's happening in hash code 2, is we do theoretically all of this great stuff where we iterate through some imaginary collection I don't show you and get the hash code of each thing, and we sum it up, so it's sort of like we're creating a hash code for a collection by summing up all the hash codes of the things stored within it. But then I return I, which just starts at 0 and counts up. So really, this just returns how many things are in the collection. Kind of. Do you see how that's happening? I know I didn't show you all of the code. But then if we come over here, like our friend said, we can see there's a lot more like complicated things happening. We're trying to get a little bit more variation going where at least we've got result, we're starting result with a prime number. And then we add, whoa, sorry, Panopto and anybody with living ears. We call hash code on each individual item. And then we multiply it by a prime number raised to I to kind of give it even more differentiation. And then we return at least result, which is helpful compared to I. But we do this thing where we mod by 5 at the very end here. So when we mod by 5, how many possible different values can this one ever produce? What is the total number of values we could produce? Yeah. 5. So what happened was we did all of this looks like research-based work, prime number, something fancy, and then we just kind of threw it away at the end. Again, I think both of these are kind of crappy pieces of code, but it was to try and get you to sort of think through. I think there's a question on your exercise that also does something similar that asks you to sort of think through the range of possible values that are created. And this is a way to evaluate how good or uniformly distributed your hash code may be. Questions on this? Whispering with no questions. Interesting. Okay, yes.
Yeah, what is it called? Like the hash code function.
Oh, thank you. This is probably something I haven't clarified a ton. So each individual object, and I do mean object, if it's something that's going to be contained within a hash table, it must include a function called hash code. So I know ints are not an object, but the wrapper class, capital I integer, it has a hash code function. It just returns the int. There is one in Java for well as string, and in fact, any object has this method inside of it. So what this is essentially saying is loop over whatever is stored in each of these collections and get the individual hash codes from them. So here, even though we're silly and we return I, if we had returned result, what we would really be returning is the sum of all of the hash codes of the individual things stored inside of wherever the heck I am, whatever this is iterating over. So if it was like an array of strings, I would iterate over each string and add the hash code of each individual string up for a final result. That's what's sort of happening there. Any other clarifying questions? Okay. Yeah, sure. Yes. Yes. And in fact, especially in Java, anything, pretty much every object that Java has made will have a get hash function. And in fact, I think I've got some, okay, great. Here we go. Thank you. So the official syntax for it is int hash code. Sorry, sometimes I call it get hash, sometimes whatever, but the actual one is hash code. This is actually just a copy and paste from the Oracle API set, but most objects in Java will already have a hash code function. And if you are writing your own object, like you do in this class, you will have to write your own hash code function so that that object can then be placed into a hash table. Otherwise, it'll say, like, I don't know, there's no hash code function. In fact, if you look at the abstract class, the object class in Java, I'm pretty sure the only things in there are that the object has to have some field and then it's got to have a hash code. So that's like the few things that Java requires that every object has. So you got to override this. I'm pretty sure. Great. One other, oh, thank you. Thanks, Pass Casey. Okay, there's an equals method and a hash method. And so the one thing you also should know is that, remember how I said hash codes have to be deterministic? If you want to implement your own hash code, you have to override both hash code and equals, and your hash code must work such that if A equals B, then A's hash code has to be the same as B's hash code. So however you implement the equal sign, so like let's say you're talking about a string, string equality is usually that you have the same character at the same location. So like capitalization and punctuation, whatever. Punctuation, I got there. Punctuation and white space and all that stuff has to be identical, right? So if two strings are equal according to the equals method, then if you're going to override the hash code, their hash codes have to be equal as well. They have to be deterministic in accordance with the equals method. Any questions about that? Yes?
Why don't we get an error when we create like a class that implements the object? Because like all like objects we create implement the object in the same.
Yes. So the reason you don't get errors is because object is at the top level of the abstract class, and so there's actually a bunch of inferred stuff that's happening from the Java compiler. In the same way, whenever you make an object, if you don't write any constructor, Java will infer the empty constructor. There's similar types of inferences to cover you in these types of moments. Yes? Is the Java hash code implementation the best out there? Yeah, certainly worth your time. I don't know. I actually don't know what their string hash is off the top of my head, but I would use Java's implementation of a string's hash code over implementing my own. If you're like, why would I implement my own? Maybe you're writing a very special object and you need to determine that. Maybe you also know something about your data set and you know where, a lot of collisions are likely to happen. For example, like you're writing a student object and there's a lot of collisions on last names, so you make sure that you include the first name as well, things like that. Cool. Okay. Great. Okay, now let's talk about this part that I promised. So we've talked about separate chaining as one possible hash collision strategy, but there is also this other general category, which is called open addressing. And what that just means is, where separate chaining was like, if two things collide to the same box, let's just let that box hold multiple things. Open addressing says, if two things hash to the same box, well, let's go find an empty box. So linear probing is when you have a table, and we are going to just use the int values themselves as hash code. So 1 will be at 1, 5 will be at 5, 11 wants to be at 1, but that is already occupied. In separate chaining, I would just add it on the, this list here. Instead, we are going to linear probe 1 to the right. And since that happens to be free, that's where 11 is going to live. Okay, then 7, its natural hash, the place it wants to be initially, is available, so we stick it in there. 12, its natural hash is occupied. So I'm going to probe again 1 to the right, and it's going to be in 13. 17, its natural hash is full, so we probe 1 to the right. 6, its natural hash is available. 25 wants to be at index 5, but it's full. So it's going to probe, and it's going to try to be at index 6, but that's full. So it's going to probe, and it's going to try and be at index 7, and that's full. And then 8's full. So it's eventually going to end up at index 9. Yes, question?
Yeah, so when you do, I guess, when you try to retrieve the value, you're giving the key, and then you hash it, and then you look for that value, and it's not where you're supposed to be.
Yes.
You know that it's actually not in the table.
Ah.
You would have to keep going, right?
So when you're trying to retrieve something, you'll call get, hash code, and you'll get the location of where it's supposed to be. If that location is full and it's not what you're looking for, then you look to the right. And if that is full, but not the thing you're looking for, you look to the right. If that is empty, then your thing's not in there. But if it's full, you keep going until you either find it or you come upon an empty space. So yes, so then this becomes a problem. Thanks, there we go. A problem can be then when you get what we call clusters. So if you have code that's all kind of hashing to the same general neighborhood, then you're right. We're going to lose that constant time lookup because it takes an iteration to find where things are and to probe. So in the separate chaining context, our in-practice runtime was kind of based on our load factor, which is like, maybe an average of how long each of those linked lists are. In this particular case, our runtime is going to be on how averagely large these clusters are. Yes, question?
Wouldn't that also make the worst case, or I guess the worst case for separate chaining open, but wouldn't it be like more likely for 5 people than if it's not a
So the question is, and you are correct, the worst case scenario for this is then linear. Like what if everything was full and the thing wasn't in the collection? You'd have to loop through everything. I don't know if it would necessarily make this worst case scenario more likely to happen, but I do think that it is more likely to impact more interaction with the object. So in the previous one, if you were saying trying to get something that should be hashed and it's all in there, then you would have to go through the end. But if you try to get something and it happens to be at another index and that index is empty, cool, then that's always going to be free. But in the linear probe, if we let it get totally full, then almost any time we put something in there, almost any time we try to grab something out, we're probably going to be incurring a lot of those iterations. And so we need to do what we need to do probably a lot more resizing in the linear probe scenario to prevent these clusters from being particularly expensive.
But I mean, like if you're trying to get something that's not in the array, don't you have to loop over the whole thing?
Yes, exactly. So if it's not in the array and we let the array get totally full, then we have an end runtime just to determine that, no matter. If the array is not full, then we loop until we find the next empty spot. And so where that empty spot is, if the array is mostly empty, chances are we're going to hit an empty spot pretty quick. That we could what? Sorry? So, okay, let's talk in this example. If I am trying to determine if the value of 90 exists in here, then I would come in here and I would realize this is full. And then I would just look to the right, look to the right, look to the right. And then as soon as I get to 3, I realize 90 is not in here. But if that cluster was smaller and I encountered that empty space earlier, then I wouldn't have that runtime. But if this entire array was full, then I would have to loop over the entire array to determine that something's not in there. So it does depend on where the gaps are. I'm not sure if that was what your question was.
Well, I just mean like, let's say for 109, the natural hash value is 9,
Mm-hmm.
but it went 0, then went 1, and put it in 1.
Mm-hmm.
Now let's say 8 got removed, then you would, when you're looking for it, you start at 9, go to 0, and then...
Oh, if you removed something from the collection, that's what you're asking about, how that would happen. Oh, okay. In this particular context, we're not talking about removal as a, like we're just talking about sort of the storage of lookup and things like that right now. Cool. Yes, question?
So my question is, because like you're like using a lot more, like you're going to the next one, you're starting to use a lot more.
Mm-hmm.
Wouldn't this take up more space? And like, wouldn't you want to use like something that's less like heavy?
in fact, great question. So, okay, how do we make this worthwhile? And so I think both of you are bringing up, why would we ever use this? It seems less efficient. I will tell you, it is less popular. The reality is that there are sometimes situations where like the accessing of the non-contiguous places in memory of the linked list make things really slow. Maybe you have a lot of extra sort of memory space. Maybe you're in a distributed system situation. And so you might find situations where these types of probing things exist. And I'm even going to show you 2 more versions of it. Is it one of those things where like engineers are kind of obsessed with hashing? And so they're going to expect you to know all the different flavors of hashing. And then you're like, cool, sweet. Which do you actually use? They're probably almost always going to say separate chaining. It's kind of like how we're all obsessed with sorting algorithms. And then you're like, cool, which one do you actually use? And they're like, quick. Great. I'm glad we had to memorize all of them. The other thing, too, is Java's implementation of hash map and hash set. Guess which collision resolution strategy it uses? Separate chaining. So this is just another option for you. But the ways to make it a little bit better, it depends on your data set, is you do need to resize a lot more regularly because letting the values fill up, we're more likely to hit those chains. So in this context, you probably resize at a lambda of 0.5 more than you let it go to 1. If you let it go to 1, you're much more likely to incur those linear runtimes. Can we do better? That felt really silly. Unsurprisingly, a bunch of you had problems with that. Okay, here's another way to do this. Well, what if we, instead of doing the like linear probing where we get those clusters and then like what happens if something gets removed, what if we plan a probe that involves gaps? Welcome to quadratic probing, where instead of just looking at the natural hash, we look at further and further away natural hashes. So we try to hash 89, that goes into its natural hash of 9. We try to hash 18, it goes into its natural hash of 8. We try to hash 49. Well, its natural hash is 9, but that's full. And then its next hash is 0, because we do 1 times 1. Boom. Okay, now we're going to try to hash 58. Its natural hash is full. So that's full, then we do +1, that's full, then we do +4, that wraps us around to 2. And what we can see there is we've now broken that cluster up with an intentional hole by doing this quadratic probing. And then 79, you can follow that patterns. And so you can see here the overall layout. We've allowed ourselves to add in a few more holes. And so also when we're going to find things, we're going to reproduce this math as opposed to just looking for the next value. And this math hopefully has fewer iterations on it than just looping through to the rightmost neighbor. Any really forward-thinking individuals see an issue with this, possibly? Ooh, yeah? Ooh, how do you know when to stop? In fact, can you know when to stop? Or could you have an issue? You actually can accidentally have an infinite loop where you just keep producing different hash numbers and it keeps modding them by table size and you keep looping around and then you just keep checking the same 4 full spots because you don't check for every open spot in quadratic probing. So when do you stop? Okay, great. So we can get an infinite loop. We also can get kind of these clusters. We call them secondary clusters here instead of regular clusters. I don't know. It sounds like a turtle-based candy or something. But we can get an infinite loop. And so to use quadratic probing, the convention is to resize when we get to a lambda or a load factor of 0.25. So this one is more likely to have even more empty space on it. Now again, it depends on your data set and the machines you're working on. There are machines that are really good at optimizing for unused data like this. Maybe that's a scenario for you. But yeah, you can tell these are probably slightly less popular collision resolution strategies. Okay, I will show you one more. I promised my friend that we have a slide at the end here. Okay, great. Whatever. Secondary clustering. Yeah, great. Okay. Okay, so then what if we just get the hash? If there is something already at its natural hash, why don't we just hash the hash? Or do something different? And this actually you will find does come up a lot more regularly, because this is a situation where maybe you have an initial hash function that takes into account, you know, a pretty good amount of information about the data to hash. Again, maybe we're talking about students and the first thing we hash is your last name. But there's definitely some last name collisions, but not a ton. So if there's a collision, then we add a secondary round, and maybe the secondary round we incorporate your first name or something like that. So we only have to do it once there's a collision, but it works exactly the same as the previous probing techniques, where we initially get our hash. If there's something already there, then we do some calculation to find a new location. So it's like a second level of calculations in response to a collision. And that is called double hashing. Questions about that? Yeah.
For double hashing, does the second hash have to be based on the first hash, or can it be using?
For double hashing, the second hash doesn't have to be based on the first hash. A lot of people will just take the hash code and then apply a hash to the hash code. But a lot of people, it depends on your data set. Like I said, sometimes they incorporate a different aspect of the data. So whatever works best for you. Now you have all the tools. You can make as crazy a hash situation as you want. That concludes our time with hashing. Come back on Wednesday for trees. Yay! See you on Wednesday. Yeah. Hey. Yes.